Alright, now 9-3, polar and rectangular coordinates. What your objective is in this lesson is to be able to convert a polar coordinate into a rectangular coordinate and the other way around. If I give you a rectangular coordinate, can you convert it into a polar coordinate? This does have some implications later on once we start working with complex numbers and finding faster ways to multiply them. So let's just start with the basics here. If we were dealing with a rectangular point or a polar point, the key to connecting both of these is understanding that a right triangle is what really ties both. What they is the only thing that they really have in common. Certainly their shapes aren't common, but if we were to picture a point on the rectangular plane here, then we have an x coordinate and a y coordinate, which means that we can create a right triangle going from the origin for one angle and having the hypotenuse end at point xy. And what's so special about this triangle is that this triangle does exist over here in a similar location, which can give us the equivalent x and y here. But also in turn what it can do for us is that we can calculate what the r is and we can calculate what that theta is. So let's go ahead and find those and let's determine some formulas for them. So reviewing what we talked about in class here, if we're going to go from a polar point to a rectangular point, what we have to keep in mind here is which direction we're going. I mean, we're given an r and a theta here and we need to calculate an x and a y. To do that, we need to do a little bit of SOHCAHTOA. Observe. Taking a glance at this right here, if we knew r and we knew theta and we needed to figure out, say, x right there, the trig equation that ties all those together would be cosine. The cosine of theta would be equal to adjacent over hypotenuse. The goal here is to figure out what x is, so if I want to get x by itself, the trick is multiplying both sides by r, and so there we have it. X would be equal to r times the cosine of theta. If we were to move on and try and figure out what y is, notice that the only thing that changes is a trig function between them. Suppose now if we were after y, the trig function that connects all of those would be sine. So in other words, the only thing that would really change when we go through and get the equation here is the fact that we're dealing with sine now instead of cosine there. So those are our two equations that we're going to use to figure out x and y. So let's see how this business gets handled now that we have these two formulas in hand. Let's look at example A right there. Let's calculate x and let's calculate y. So x would be equal to 5 cosine pi over 3. Your next move would be to figure out what the cosine of pi over 3 is. You can use the unit circle to figure that out. So now we arrive at our final x coordinate here of 5/2. Let's move on to y. Now we say that y is equal to 5 sine of pi over 3, unit circle. Usually if 1/2 is attached to cosine, square root 3 over 2 is not too far behind, is it? So there we go. Now when we have those x and y now, we can write our final x and y coordinate of 5/2, 5 square root of 3 over 2. Let's take a look at the other one. Not much else is different here. The only thing that's going to stump us now is that we just can't come up with a exact answer here. So let's just rattle through them. Alright, so there we go. We got negative 4.4 for x and we got positive 12.2 for y. So our xy coordinate this time, negative 4.4 and 12.2. Here's a great thing to check to see if you've got the right answer. One thing that you should always do is check both quadrants in each one of the start of the problem and the beginning of the problem and the end of your problem. So if you look up here, note if we're going to try and plot negative 13, negative 70 on a polar graph, realize that we'd have to spin ourselves pointing this direction here down to negative 70. Probably do a little better than that, couldn't we? Negative 70 would probably take us a little bit further down this way. But then again, remember, because it's negative 13, we have to go back, so we'd end up here in the second quadrant. Do the same thing here. If we had to plot an x and a y, and we had to go negative 4.4 and 12.2, we'd be up here in the second quadrant too. So always double check your quadrants to see if you're going to end up in the same quadrant. And you have to end up in the same quadrant. If you don't, you didn't write the point down correctly, so you're going to have to double check your math there. Alright, let's try and go in the other direction now. So if we were going to go now from rectangular to polar, getting the r and the theta individually is really pretty simple too. Understand that if you're given x and y, you're given two sides in a right triangle. Remember, r was the hypotenuse in that right triangle. So to find the hypotenuse, x squared plus y squared equals r squared, Pythagorean theorem. Working with that same triangle, if we're going to try and find theta now, we're using SOHCAHTOA here. What ties theta and x and y together would be tangent. But remember, thetas are unknown this time, so to unlock what the angle is, we need to use inverse tangent. Now, one extra piece of info that you're going to need to pay attention to is we're going to want to pay attention to what location that rectangular coordinate is, because sometimes inverse tangent won't give us the true answer. Inverse tangent only gives you answers from negative 90 degrees to 90 degrees, which means that they're only going to give you a point in, say, the fourth quadrant as well as the first quadrant. There should be a less than sign there. So because it has that little bit of a shortcoming with it, you're going to have to add 180 to any angle that you get there to pick up one that would be in the second or the third quadrant. You're also going to have to pay attention to what mode you're dealing with or what kind of measurements you're dealing with, whether they're radians or degrees. So let's take a look at these examples. Alright, so the natural decision to make on these coordinates is to find r first, which is Pythagorean theorem. So let's go ahead and do that with this second quadrant point here of negative 2, 7. So a squared plus b squared equals c squared. Doing all of that work there leads us to a r value of the square root of 53. Next, it's inverse tangent. Taking inverse tangent here, keeping in mind that we had to stay within the world of radians here, unfortunately, leads us to a theta angle here of negative 1.29. However, notice here that our x coordinates are negative. In other words, we're in the second quadrant. And when we're in the second quadrant, like this one here, or in other words, when x is negative, we have to add pi to this angle, which now lands us at the proper angle here of 1.84. So one more time, the reason why we have to add pi to this form here to get 1.84 is when inverse tangent does its thing here. You know, that minus sign could be anywhere. What the inverse tangent function actually does here is it incorrectly puts you right here, going 2 to the right and 7 down. When really what we wanted to do is we wanted to go 2 to the left and 7 up. So the connection here is that inverse tangent gave you that angle right here, when in truth we want this angle right here, this obtuse angle there. So how we correct here whenever we're in the second or the third quadrant is we take whatever angle they give us and then we just simply add pi to it to arrive at that angle right there. Okay? So that's our final answer there, square root of 53 and then 1.84. Now when we move into the first quadrant point there of 3, 6, note that we won't have to do this pi addition maneuver here. First quadrant, Pythagorean theorem, let's get that first. Alright, so we got that one now. It's time for inverse tangent to find theta. Notice this time that we do not have to add pi here because that x value is a positive value here. We're in the first quadrant. So the angle that we see here is the angle that we get to keep. So now let's just write our final answer. Alright, so first quadrant we don't need to add pi, but if you think back here, second quadrant and third quadrant, like the next one that we see here, that third quadrant point over there, -5, -1, we're going to end up having to add pi to it. So getting r is pretty straightforward. Once again, Pythagorean theorem. Keep in mind that when you square your negatives, make sure you keep them positive. Rocking and rolling now with inverse tangent, we get 0.197. Keep in mind that we're given a first quadrant angle there with inverse tangent, so to compensate and get us to the third quadrant we need to add pi. And so there's our final answer. Over there in the fourth quadrant, same routine. Pythagorean theorem, keeping in mind we have the square root of 80, so we can simplify that into 4 square roots of 5. Inverse tangent. Notice here that inverse tangent gave us -1.1. Now, notice here that I had to add 2 pi here. The reason why I'm adding 2 pi to this is because we got a negative angle here, and the stipulation said here that we wanted a positive angle between 0 and 2 pi. So to fix that and still keep the same coterminal angle, we needed to add 2 pi. So now we arrive at our final answer here of 4 square roots of 5 and 5.17 for our direction.